Hello and welcome, handyman's astronomers. We're gonna talk about the rDUINOScope today. The rDUINOScope is an open source control pointing and tracking telescope device. This system was initially developed by Dessislav Gouzgounov in 2016. Since many actors have developed the system both in terms of software and hardware. The main component of the system is an Arduino Due with an ERRATUM CPU. The rDUINOScope has a GOTO system and it identifies its position with the GPS module. There is also a manual control with an integrated joystick. Here I choose RJ45 connectors to plug the motors because it's nice, secure and easy. On the box there is a little switch to turn it in night mode to not be blinded by the screen when you are observing deep sky objects. In the system there is an accurate clock. There is also a humidity and temperature sensor, a Bluetooth module to driving it by a PC or smartphone. Then we have access on all the Sky Safari and Stellarium database. In the rDUINOScope you have an inbuilt map to look where the telescope is pointing. An internal database contains the 250 best objects in the sky, like the Messier objects and a part of the new general catalog. It's able to tracking after a GOTO pointing, it can do a meridian flip, and it can stop when the object is below the horizon. Here you can see the GPS initialization. Let's take a look in the menus to see the functionalities. After the GPS initialization page, there is a date and hour page. This can be set and recorded in an RTC chip. Afterward, there is a calibration page with 2 modes of alignment to align the telescope on the sky. As you can see, there is a 1-star alignment and an iterative alignment. The next page is the main page of the rDUINOScope. You can here load some object, like the Messier object. You have all the catalog of the Messier object. There is also hidden treasure with some NGC objects. You have the solar system with all the planets, the sun and the moon, and a custom catalog. You can create your own catalog stored in the SD card. In the home position, the telescope is pointing on the celestial north. It is possible at any moment to launch the tracking on the right ascension. When you activate the Bluetooth on the rDUINOScope, this one is listening all the device around, then you can drive it with a smartphone or a PC with Bluetooth. Some statistics data are available on the stat page. These ones are stored in the SD card. You have the location generated by the GPS, you have the humidity and temperature, and the list of the objects observed. This page shows us where the telescope is pointing. There is also the position on the map. You have the actual position of the telescope on the sky. You can use 2 fans to calibrate the temperature of the telescope. These ones are supplied by 5 volts. There is also an option page. It is possible or not to activate the sound. You can activate the steppers for the driving motors and the focuser. If you don't have a focuser, let it on off. There is a brightness option. You can say the screen to stop after 30 seconds, 1 minute, 2 minutes, etc. or never. There is 3 modes of tracking: celestial, solar on lunar, and you can set the meridian flip auto or off, and you can return here on the GPS page. Let's take a look now to how build this version, which is the Khairey Nouhe version. This version is very interesting because there is many additional functions compared to the original version. Here we go now with the list of the needed components. The first component is the screen. The screen is taller than the original screen. This is a native fruit, you can see the reference there. This is a 3.5-inch sensitive screen. You have on the back a place to put a micro SD card. When I shot this, I did a fail. This is a micro SD card and not an SD card. We're gonna see later what we have to put inside this card. Next thing, it's the Arduino Due. This is an Arduino card with an ARM processor. The board looks like this. You have a bunch of pins to do what you want. This is an Arduino Nano for the Autoguiding part. This little board will be an external device to make a bridge between PHD2 software and the rDUINOScope. This Khairey Nouhe version is interesting for the Autoguiding function. We continue with the Bluetooth module. This part is very interesting because you access all the catalog inside Stellarium or Sky Safari software, so you can go to any object of the NGC catalog, for example. This is a buck converter. This is a voltage converter. For example, you have a 12 volt input and you can adjust the output voltage. For us, we're gonna set it up at 5 volts because the Arduino Due has not enough power to supply all the stuff that need 5 volts. This is the joystick module for Arduino. This is a rotary encoder. This one is a 20 pulse by revolution. It's mounted on a PCB and it's designed for Arduino boards. This is an on-off switch for testing purpose. I replaced it by another on-off switch. This is a 1 watt 8 ohm little speaker, very small and works very well. Here we have the GPS antenna with the PCB board and the little antenna. We put the antenna with a little metal drop side up and the bottom face is a shield. This is the RTC module, real-time clock, to store the date and hour. It needs a little battery. This is a CR2032 battery. Next we have the temperature and humidity sensor, DHT22, with 4 pins. Now let's take a look at the drivers. This is Polulu DRV8825. Comes with a little aluminum heatsink. I replace it with bigger heatsink for better thermal dissipation. If you purchase it on AliExpress, make sure you have the TI logo on the main chip. There is 3 drivers for the 2 motors and the microfocuser. This is a pack of resistors that I already had. We need several resistance that you can find on the wiring diagram, and at the end of this part I've put a table with the references. This is a small value resistors pack because we need a 6.8 resistance, which is difficult to find. Then we have capacitors. We need 2 types of capacitors, 100 and 330 nanofarads. This is the 78 09 MOSFET. This is a transistor for the voltage regulator. We build a voltage regulator with this transistor and the two capacitors we've just seen. Next, this is a transistor pack because we need several reference of transistors. You can find at the end of this part the list of all the transistors you need. Let's take a look at the RJ45 connectors, 2 on the motors, 2 on the rDUINOScope for the motors, and 2 for the microfocuser. For each one you have the connector and the micro PCB. You have 8 pins on it, and when soldered on the micro PCB you have all the pins in line. There is 4 wires on the NEMA motor, so I've soldered the pins 2 by 2. Then 2 wires on the RJ45 cable is more comfortable for the current. Then we have the RJ12 connectors for the auto-guiding part. This is the same connectors as the ST4. You should not be confused with the telephone sockets, which have only 4 wires. Here I choose 2 jack connectors to eventually plug 2 fans to calibrate the temperature of the telescope. Here we have the PC81-7 optocouplers. These are used to electrically separate 2 circuits. We use that for the auto-guiding part, then we can separate the Arduino Due and the Arduino Nano. We use one component for one wire of the auto-guiding, then it's more secure to not damage one or the other. Some wire, we need wires. I have DuPont cable, male, female, female, etc. in several lengths, 10 centimeters, 20 and 30 centimeters. If there are too many, it's always useful. I've bought a breadboard, very useful to test without soldering, and a universal PCB. I've ordered several sizes, but I've used only 2 boards of 5 by 7 centimeters. 2 NEMA 17 motors, you can see the reference right over here. This is 4 wires motors, 400 steps and 1.68 amperes by wire. The 3D printed motor holders, this is very good quality and very good price, printed on ebay3d.com. Found it on the OnStep website. This is already existing models that has been modified by Mr Khairey Nouhe to have a rectangular hole for the RJ45 port. You're gonna find the Thingiverse addresses at the end of this port. This is RJ45 flat cable in 1 meter. I think 1 meter is a bit short. 1.5 meters would have been better. The pulleys. This is 48 teeth pulleys and 16 teeth pulleys with a reduction factor of 3 for better precision. Beware of the hole diameters. I made a mistake initially, because the hole needed for my EQ5 was 6 millimeters and the hole was 5 millimeters, so I had to drill it to enlarge the hole. This is GT2 pulleys with 6 millimeters thickness, and the belts, this is GT2 6 millimeters belts in 150 length, but the 148 centimeters length was the better size for my NIQ5. We need some screw. The list of the screw is at the end of this part. I've ordered this on Bricovis in France, which provide very good quality inox, and shrinkable sleeve in several diameters. I don't short all the components, and you're gonna have a complete list just next. So let's get started with the software part. To download the software which will be flashed into the Arduino, we go on the GitHub page of Khairey Nouhe and the rDUINOScope with Adafruit version. By scrolling we can see this version is fully updated and it's pretty complete. To download the file, don't go to GOTO file, but go to code and download zip. So we are in the archive we just downloaded. There are several folders. Arduino Nano firmware is the firmware for the Arduino Nano for Autoguiding. Then we have an ASCOM driver, Arduino ST4 driver. After installing that, the Arduino Nano is recognized by PhD2 as Autoguiding peripheric. So the installer is in this folder. After installing that on your PC, you can use it with PhD2. The how to set up the ASCOM driver. Then we have a library folder with all the libraries needed. We're going to move these libraries into the library folder of the Arduino software installation directory. Next, this is the sketch folder with all the code of the rDUINOScope. The main code is right here. Next, this is the SD card content folder. We're going to move all these files into the micro SD card. Next, this is the wiring diagram with all the components needed. This is the great version of Khairey Nouhe. Then we have an Excel file for some calculation. I didn't use it. I just replaced some variable in the code. We're gonna see that just next. We put in the code the number of the teeth for each warmth of the mount. So now I'm gonna copying all the files and the SD card content folder of the rDUINOScope file I downloaded in the GitHub page of Khairey Nouhe. So copy all the files and paste it in the micro SD card directory. Then you have to plug the micro SD card on the back of the Adafruit screen and that's done. If we take a look inside this folder, we can see there is picture for day and night mode for each display, star map, the user interface and the objects, etc. You have some Excel files for Messier, Treasure and custom catalog. Next we have to download the Arduino software. Take the Windows 7 and newer to have full access on the directory, because we have to move some files in the installation directory. When the installation is completed, you go into the directory and open the library folder. Then go into the rDUINOScope folder you just downloaded and open the library folder. Then you have to copy and paste all the files into the library folder you downloaded into the library folder of the software. When it's done, you can open the Arduino software to flash the board. Then we are in the Arduino software. You go into type of board and the board manager. Then you scroll down to find the same boards with ARM processor, because this is the plugin for the Arduino Due. I've already installed it. That's why I have a delete button. You're gonna have an install button, so install it and it's done. Then we plug the Arduino Due board onto the PC and we open the software and do Tools, Board Type, Arduino ARM and Arduino Due Programming Port. Then you go to Tools, Port, and you select the good COM port, the one connected to your Due. And just verify I'm on the good Arduino USB port. That works too with the other port. Make sure you selected the good port into the software. Then open the main code file, which is beside all the function codes, and click open. And you can see it open all the function codes, which are in several tabs. So you can see now the code of the rDUINOScope, which calls some functions which are in the tabs. So now we're going to modify a small part of the code to match with our mount. We have to enter the number of teeth of the worms in the mount. For me, I have an NEQ5, it is 144. This is here the default value. The reduction factor of the pulley, here I have 48 divided by 16, so 3. The number of steps of the motor, 400, and I don't touch the microstep mode. This is the only thing we have to modify. Then we click on upload to upload the code into the board. We're gonna see later that I had modified some parts in the code because some function wouldn't work very well, in particular the Autoguiding part and some other stuff into the hardware. We're gonna see that later in a troubleshooting part at the end of this video. So let's get starting with the soldering. I've soldered some pins on the screen to plug in some DuPont cable, and don't forget to make a bridge on this part with some soldering. It is necessary to activate the SP mode in this version. I soldered the mini PCB on the RJ45 connector, then I tested it with a cable plug in it and a multimeter in on position to see if the current is passing through. Then I soldered the 3 connectors on a universal PCB. The 5 by 7 cm was just the right size. Then I tested the solders to find if there was eventually some bridges. The same method as seen before, with a multimeter in on position. And the same thing with the cable plugged in the connector 2x2 to see if the current is passing through. Then I soldered the 3 drivers. If I had known earlier, I will have soldered sockets to plug the drivers, because if one of it's blow, it will be a mess to unsolder that. After I soldered the pins of the RJ45 2x2, then with 2 wires, the cable will heat up less. Then I started to solder the RJ45 connector on the drivers. So here we have the 4 wires of the motors coming into the 4 entries of the drivers, and do the same for the 2 other drivers. Then I soldered a black wire for the ground and a red wire for the VMOT to supply the motors. Then I bridged the sleep and the reset pins of the driver with a blue wire for the 3.3 volt supply. Then I took some 30 cm DuPont wires and I cut the end to connect the other pins of the drivers. I made 3 like this for the 3 drivers. Here we have all the pins on the side of the driver connected with the DuPont cable end. It will help us when we're gonna use a breadboard. So I soldered the 4 wires of the motors to a RJ45 connector 2x2 as we've seen before, to make the current going through 2 wires, and then later I've inverted some wires so I'll let you see the final version. The next part is the made of the fans connectors. To make the fans connectors we need some components. As you can see in the wiring diagram, we need a transistor, a resistor and a capacitor. I've cut the transistor middle pin, then I soldered the resistor on it. Then I used a little piece of hitch and cobble sleeve to isolate the pin. After that I've soldered the capacitor on the transistor. You can see after I removed the tape, it's soldered between the resistor and the emitter of the transistor. Then I soldered the free leg of the transistor on the ground of the jack connector. I soldered a black wire on the emitter of the transistor. This is the left leg when you look at the flat side of the transistor, and the colored DuPont cable on the middle pin. And I soldered a red wire on a free pin of the jack connector. Now let's take a look at the Autoguiding part. I soldered color wires on the RJ12 connector and identified the colors. I used for that the standard 84 pinout. I tested all the wires to see if there was bridges. I isolate the wires with some hot glue to prevent them from breaking, because this is tiny solders on this connector. I took the PON cable with the same colors. I've placed the 5 optocouplers with the 100 ohms resistors. Please beware of the locator, the little round in the bottom left corner. I soldered the resistor on the optocoupler pin, the one which is in front of the locator. Some red wires bridges for the 3.3 volts. I soldered the colored DUINOScope cable on the other pin for the input. I made some black bridges for the ground. Here we have all the grounds connected to each other. If we take a look at the wiring diagram, we see we need a grounded 4.7 kilo ohms resistor on each wiring input. But if we look at this part, we see the ground is very close to each input. So just place the resistor like this. I placed all the resistors on the input cables. I've already soldered this wire, so it was a bit annoying. I placed the leg a hole further away so I don't have to go through the solder again. Then I connected the leg of the resistor to the leg of the optocoupler. And here we have the wires soldered coming from the RJ12 connector. I soldered the ground black wire of the RJ12 connector to a place of the board with the big black wire on the same place to make the general ground. At the back of the board I soldered the 3 black wires, the grounds of each driver, to this main ground of the board. I soldered a big red wire for the main 12 volt of the board, and I soldered the 3 red wires of the VMOT of the drivers. I did the same for the 3.3 volts blue wires. Then I placed the blue wire coming from the main 3.3 volts input of the board to the start of the 3.3 volts bridges of the optocoupler for the Autoguiding. Here you can see a wiring diagram for the Autoguiding with the ST4 cable on RJ12 connectors. I've simplified the original diagram by deleting all the LED stuff and maybe in the future use a real ST4 camera. You're gonna see later that my first Autoguiding test was done by another juice cardboard with tape, so at the end I've put this Arduino Nano in a box with on the side the USB connector and on the other side the RJ12 connector to plug in the rDUINOScope. Let's take a look now to the power supply section. If we take a look at the wiring diagram, we see there is a voltage regulator based on the 7809 transistor and a part with the monitoring of the battery. When we merge the 2 circuits, we obtain this one. We're gonna use this circuit to power supply the rDUINOScope and do the monitoring of the battery. I placed the resistor for the monitoring, but I hadn't 26K resistor, so I used a 20 and a 6.8 resistor. Here we have the DUINOScope cable for the monitoring input. Then I placed the 7809 and the 2 capacitors like this on the 26K resistor side. I soldered, this is big solders, but I say to me, maybe there will be a lot of ampere into that. The 2 power supply cable to plug in the battery. The central pin of the 7809 grounded. Adjusted the buck converter with a little screw to 5 volts, so I soldered the buck converter on the power supply board. At the output of the transistor I have a 9 volts yellow wire. I soldered the 9 volts and the ground on the side of the buck, and on the other side I have a red and black wire for the 5 volts. So with this power supply board I have 9 and 5 volts to supply the rDUINOScope. I moved the 10K resistor to let it take less space. These three black wires are the ground. The ground pass through the buck and go on the other side. And on the top I have the transistor with the 9 volts output. After cutting the edge, it will take less place. Let's take a look now to the joystick wiring. We see on the diagram we need 147K resistor mounted like that on each joystick input. At first I used thermal deployable plugs and I soldered on it 47K resistors. Then I took 3 wires and I soldered like that the 100K resistor. Did the same for the 3 wires. Put some heat shrink sleeve and assembled the 3 legs of the 100K. We put a red wire on the 5 volts input and the ground is connected to the 3 legs of the resistors. Then we soldered a black wire for the ground with a little piece of heat shrink sleeve. Here we have the joystick finished with all the resistors in the plug. We have the 3 legs for command, the black and red wire for power supply in 5 volts, and the 3 depot cable to plug into the Arduino. Let's go now with the switch which allow us to go between the day and night modes, and we're gonna use 2 330 ohms resistors. So we soldered the 2 resistors on the middle leg and one of the 2 external leg of the switch with the red depot cable soldered directly on the leg of the switch. Then I soldered the blue wire on external resistor and the black wire on the central resistor. Some heat shrinkable sleeve to isolate. Then I have the blue cable for the 3.3 volts, the black for the ground, and the red to plug into the Arduino. Let's take a look now to the wiring of the speaker. We're gonna need for that some resistances and a transistor. I soldered the red wire of the speaker to a 6.8 ohm resistor on the collector of this transistor, you have the reference here, to the ground. Here I soldered a black wire to the emitter of the transistor. Don't forget the sleeve, I have to desolder it. Then I soldered the 220 ohm to the base central pin of this transistor. Here you have the wiring diagram with the 6.8 ohm resistor, the speaker, the transistor, the 220 resistor, the wire to the ground and the wire to the Arduino. Some heat shrinkable sleeve and we have the final wiring of the speaker with the transistor. On the top you have the wire for the ground, on the bottom you have the wire for the plus 5 volts, and on the top here we have the wire for the Arduino. Here we have the temperature and humidity THT22 sensor. We put a 10K resistor like this. We bend the 3rd pin on the back because it's not used, and we put the cable like this, not particular difficulty. Here we have the wiring diagram. It is not supplied by the buck converter, but with 3.3 volts Arduino. You have the data out to pin 43, the not connecting, and the ground. I've not shot all the soldering because there is no particular difficulties on the Bluetooth module. You power supplied by the 5 volt buck converter. You have a wire for the ground, 2 wires to the Arduino. Memory card is not used in this project. You have the rotary encoder with a wire to the ground, powered by the 3.3 volts Arduino, 3 wires to the Arduino. You have the GPS module powered by the 5 volts but Arduino, not buck converter. You have a ground wire and 2 wires for the Arduino, and the NTC module is 5 volt buck converter power supply and a wire for the ground, 2 wires for the Arduino. So we're gonna take a look now to the first rDUINOScope power supply. I have here a 12 volt power supply. I plug it on the two input wires to the voltage regulator, the buck converter. I have here the two outputs, ground and 5 volts on the breadboard on separate lines. I have the 9 volts main coming from the voltage regulator. I have the ground, I have the 3.3 volts emplacement reserved, and also for the 5 volt bucks on Arduino. Here this is the cable for the monitoring on the A7 pin. I plugged here 3 wires for the ground, the 5 volts and the 3.3 volts. They go to the breadboard at the emplacement. One for the 5 volts Arduino, for the 3.3 and the ground. And I will plug the modules on this breadboard on this emplacement to power supply it. So I put a wire on the V-in pin of the Arduino coming from the 9 volt main, because we can supply the board like this. Here we have the first boot of the rDUINOScope after methodically placing all the modules on the Arduino for the input pins and the breadboard for the power supply pins. So for now there is no motors plugged on it. We're gonna see now what we must do before plugging the motors. So I have here a voltmeter and the black wire is on the ground of the circuit and the red wire is connected to a screwdriver. We have to adjust the voltage reference of these drivers to the half of the max amperage by coil using this screwdriver. So we carefully put the screwdriver on a little screw on each drivers. Here we have the default Vref value, which is equal to the max amperage by coil. So I'm gonna adjust it to about the half of this value, so 0.84 volts. I mentioned here there is no confusion between amperage and voltage. This is the weird procedure for adjusting these drivers. And now I'll let you see the boot of the rDUINOScope with the motors plugged. As you can see, it's working perfectly because after slewing the target, the array motor is entering into tracking mode because you can see it spinning at a very slow speed. Now it's time to get some miniaturization to let it fit in the box. To do this, I used the second PCB and I soldered some pins to go into the bottom of the Arduino board. And it will be placed like this to have a gain of place. And I soldered the colored Autoguiding wires on the corresponding pins. The ribbon you can see here, it's the wires for the focuser. On this ribbon there is only 3 wires used. And as you can see, I also soldered 2 wires for the declination and ERRATUM control. Here we have the screen. I removed the pins and soldered directly the wires to take less place. If you take a look at the wiring diagram, you can see there is many places on the board to plug the screen. The pins are not aligned on the same place, for example. So I routed all the cables from the Arduino to the new PCB to have all the pins on the straight lines, and I soldered the corresponding wires from the screen, so it will be much better to put it in the box. Here I soldered the 3 wires for the rotary encoder. A really good stuff to look well at the solders, and I'm pretty sure you have one. This is an eyepiece. Here with the 25mm eyepiece, you are pretty sure there are no bridges. Here I soldered the 21 pin of the Arduino, the blue wire, to the blue wire of my screen, which is the first wire to be soldered. Here we have all the wires of the screen soldered to the corresponding wires coming from the board, and in the bottom there is the 2 grounds of the screen soldered in a ground path and made on the PCB. So at this time the only thing I have to solder now is all the modules power supply, so I placed it on the breadboard to test my new solders. So at this time I did some extensive tests, such as GOTO, use of the joystick, testing the output jack for the fans, the Bluetooth module, the rotary encoder, etc. And when all was good, I was continuing my soldering. Here you have a look to the test of the output jack for the fans with the on and off position with a multimeter. So I placed all the stuff in a cardboard box with the same dimensions as the one in plastic I ordered to see if all can go in the place. So here I have all the power output of the board, the ground at 3.3 volts, 5 volts, etc. I have here a path for the ground. Here I have a wire for the ground. I have some wires for the 9 volt main, the 5 volt buck, the ground, etc. So here I place the GPS module with the antenna on the top, like it will be in the future box. So I have here the red wire which power supply the drivers below. I'm gonna solder it directly on the input. So and the 12 volts on the red wire here. So it's gonna supply the VMOT of the drivers with the 12 volts of the battery. You can see now it's down. The red wire is directly connected to the input. And here the white wire is the wire for the battery monitoring connected on the D7 pin of the Arduino. The yellow V main going to the V in. This is the ground of the optocoupler circuit, which is soldered on the ground path, for example here. Here the soldering done. Here we have the 5 volts and the ground coming from the buck. I solder the ground here. So here I connected together several grounds. The grounds of the switch, the ground of the rotary encoder, the ground of the GPS module, and I have here a wire going to the PCB, soldered on my ground path, which is turned on now, and I have a black ground wire going to the power supply. Now we are about to solder all the 3.3 volts cables. Here I have the switch. There is another one here for the screen. You can see the wiring diagram to not forget one of them. This one is for the rotary encoder. There is another one below here coming from the optocouplers for the Autoguiding. So I made a big drop of solder and soldered together all the wires. One thing I forgot, it is the DHT22 with the ground connected here and the 3.3 volts connected on the big drop of solder. We have the rotary encoder soldered on it. You have the yellow wire here for the optocouplers. here we have the blue wire for the switch, powered in 3.3 volts. And all these wires are connected to this green wire to the 3.3 volts of the Arduino. To save some place, I've connected the two black and red wires of these jack connectors to have only two wires for the power supply and the two wires for the Arduino board. I've put some hot glue and tape to isolate the two jack connectors. So I put the two jack connectors on the top, maybe on the final version they will be on the side. They're gonna be supplied in 5 volts buck. As for the speaker, the joystick is in 5 volts Arduino, the RTC module is in 5 volts buck, the Bluetooth module in 5 volts buck, the GPS module in 5 volts Arduino. Here I have the ground and the 5 volts buck coming from the speaker. I have different wires here and ground for the different modules, and I'm gonna connect all that stuff on the PCB. So here I have the ground for the two jack connector here going to my ground path, and I have another wire here which is going below to the ground plug of the Arduino. Don't forget to connect all the grounds of the circuit. So now I'm gonna connect all the 5 volts buck powered supply modules on this new path on the PCB. Here is the first one coming from the speaker. So now I'm gonna link all the 5 volts buck wires, the Bluetooth module. This one coming from the jack connectors. This one is for the RTC module right here. This one is for the screen, and all this stuff will be connected to this wire, which is the 5 volts buck power supply. I'm gonna do the same for the 5 volts Arduino, so the GPS module. This is the wire for the joystick. These two wires will be connected to this wire, which is the 5 volts Arduino output. The wire to connect the screen was a little short, so I made a second path coming from the main path of 5 volts buck. Here I soldered the wire for the Bluetooth module. Here you have the wire coming from the RTC module. The 5 volts buck here is soldered on the side. Here this is the 3 wires for the 5 volts Arduino. The wire coming from the GPS. Here you have the wire going to the board, to the 5 volts output, and this is the wire for the joystick. I also soldered the ground and I extended the wires because they were a little bit short. So I stopped now to explain something. I've soldered the black wires, the grounds of the rotary encoder and the GPS module to the ground of the switch, but I've soldered it above the resistor, and the wire below was going to my ground path, so I had a resistance in the ground, which is not good. So I removed the solder and soldering the two grounds of the rotary encoder and the GPS together to a big wire, because we need a strong wire for the ground of the GPS module. So the next step was to mount the rDUINOscope on my NEQ5 to test it on the mount. This is all the 3D printed covers and the screws. So there is a fixing plate to mount like this, and there is a cover, but it's not adjusting quite well because of the worm, so I have to drill it. This is the same for the two covers. Here we have all the stuff mounted on the mount. I used a 150mm belt, but at first they were a little long. I replaced it by shorter ones. And here we have the rDUINOscope running, ready to go to the first test. So now the mount is entering in tracking mode. Let's take a look at the map to see if it's pointing in the right direction. It seems to be okay. The next step is to test the mount with the load with the tube and the counterweight on the mount. So the motors need the torque to move like expected, and here it seems to be okay. Some final adjustment. I glued the RJ45 connector on the two holders. The 7809 was very hot, so I decided to make a dissipator. Here I have an aluminum plate with some thermal paste. I extended the dissipator of this component. I soldered 100 microfarad electrolytic capacitors because it is recommended by the manufacturer to protect the drivers. These capacitors are mounted between the V-mode and the ground of the drivers, closest as possible, and beware of the polarity. Now I'm starting to put it in the box. I reset my box and started to make the apertures. It's relatively easy with the cutter, with the driller, to make the holes. I had finished my box. Here you have the RJ45 emplacement, holes for cooling the voltage regulator. You have holes on the left side for the DHT22, holes for the speaker, holes for the jack, hole for the RJ12 connector for the Autoguiding. The RJ45 coming here, and I have an aluminum bracket to maintain it because the solders are very fragile. On the top you have the hole for the rotary encoder, the hole for the GPS antenna, the module coming on the right side with the holes to see the LED status. You have the hole for the switch. There is the hole here for the joystick, the hole for the jack connector for the power supply. On the top I made some holes, but I resealed it because I don't want to have some fresh air coming from the top. Here I have the USB cable to programming the board without a mount hole. I mount the joystick like this, with only screw and bolts. Make sure it's not rubbing on the sides. I removed here some plastic because with the solders of the screen there was a little space when I wanted to mount on it that was not adjusting quite well. Here you have the screen mounted on the top cover. Here I mounted several modules. Here we have the new switch ready to glue. I mounted the connector for the power supply. I fixed the solders by hot glue to protect it. Here I had to drill the PCB because there is an emplacement for the screws. The three others are clear. Here we have the RJ45 with the aluminum bracket fixed. For the PCB I'm happy to have not soldered something on the emplacement of the new hole. So here we have all the components mounted on the box. The cable for the flash, the rotary encoder, the GPS antenna, the connector for the power supply, the switch, the hole for the GPS status, the joystick and the screen. On the other side you have the 2 jacks connector, the humidity sensor, the RJ12 for auto-guiding. I've added some little in-sync for better cooling performance. I've installed the same on the drivers. One of them on the aluminum plate isn't holding, I hadn't kept it. So this is aluminum heatsink like this one. So now I have a better cooling performance on the 7809 and the drivers. I've also installed a 5 volts fan. This is a radial fan mounted directly on the 5 volts buck. I've made a hole on the side for extraction, and on the bottom side you have the aspirating holes and the space between the RJ45 connectors to cooling the drivers and the power supply board. The holes on the top that I reseal because I don't need to have fresh air coming from the top because there is nothing to cooling. And here we have the box completely finished. So I made a holder with the angled piece of plastic and glue. To attach it on the support I use a clamp made for GoPro cameras, and I put a little magnet on the back to have a very good maintaining of my rDUINOScope. And you can see here the rDUINOScope mounted on the telescope for our first test outside at night. You can see a quick overview of the Bluetooth mode. After activating the Bluetooth mode on the rDUINOScope and the phone, you can see here on Sky Safari where the telescope is pointing. I was on M13 and I can now selecting any object in the database to go to on it, and this way you can access a bunch of objects. Maybe there is some disconnections of the Bluetooth, but it doesn't matter, you can reconnect it when the GOTO is finished. You're gonna see now the telescope is pointing right in the object. Let's talk about power consumption now. At first the drivers was set at the maximum value, and at idle we observe a consumption of 0.3 amperes. Here with the stepper motors on and no tracking, with the GOTO 1 motor, with the GOTO 2 motors, this is a little bit more, when tracking on array. After that I tried to lower the driver's voltage to lower heat and consumption. I had to drill the PCB to access the driver's screw and restart my test. So at idle this is the same. When GOTO with 2 motors it's about 1 ampere. When the drivers was set at default it was 1.3 amperes. When tracking it is 1 ampere, we were at 1.2. When I add a fan there was a little bit more consumption, so let's take a look at that. I decreased just a little bit more the drivers to 0.65. There is a slight increase in idle, and when you are in tracking or GOTO with 1 or 2 motors, it's always about 1 ampere, and I am now with the mount at full speed and better cooling, and the rDUINOScope is consuming just 1 ampere. This is a power consumption reduction of 20 to 30% comparing to the default values. Now let's take a look at the troubleshootings and how to solve the issues. The first problem was the motors were stuck in place. They wouldn't spin at all, making a high-pitched noise, and that's finished by crashing the UI. To solve this issue, you must supply the motors by the 12 volts input directly from the battery instead of using the 9 volts output from the voltage regulator. I also had a stocking issue of the screen, but it was because of the memory card. I replaced it by a quality one and there was no problem anymore. Here that we are near the crash. Here we have some jumping steps with crackle. The motor is in tracking, but it makes some come and go. So I took a DuPont cable, I bridged these two parts of the circuit on the ground and the problem disappeared. This was because of a too weak ground, so I double the ground with this big wire and I double also the 5 volts buck path because it was too thin too. So this is the final result. You may have noticed that when you've seen the video. And we can see now there is no problem anymore. Another fairly common problem that I've seen many times in the Facebook page. This is where the behavior of the motors when you use the joystick. I seem to add or change the resistors value, but that wouldn't work for me. I just have to go in the code to resolve the problem. By default, when the joystick is pushed to the stop, it works in full steps, so there is 1 here. I replaced the 1 by a 2 because the intermediate position works quite well. After that, the joystick works normally. There is 4 values to change on the 2 axes and the 2 extreme positions. We replace all that by a 2 and we see now the joystick is working perfectly. Another problem was continuous pulsing. I did first test with Autoguiding mode and seen there was a continuous pulse on deck minus. So I had an idea to debug it. I've added some lines on the code to display the status pin of the Autoguiding pins. I was inspired by the button displayed on the Autoguiding mode and I replaced the value by the status pin. The advantage of this is you can see the status of the pin directly on the screen when you are looking at the solders to resolve the problem. After that, some hot glue to fix the bad solder and it was okay. This firmware was only for DIAG purpose, so I refreshed the original firmware and all was okay. Another issue was the tracking stop when plugging the ST4 cable. So the guide star was going out the field as soon as I plugged the cable on the rDUINOScope. So I went in this void loop section of the code to comment these 3 lines and the other 3 lines on the bottom here to reactivate the tracking when you enter in Autoguiding mode. So after that the calibration succeeded and the software managed to follow the star. At this time I'm not sure the Autoguiding is working perfectly because my setup wasn't very robust. Maybe I have to revise the code because for the array I'm not sure that adding pulse or add array minus pulses will correct the periodical error. Increase or decrease the speed will be better. At this moment it's uncertainly, but it may be settled before the end of the tutorial. Another issue I had with the joystick, it was when I pushed the joystick in the bottom to the stop in array, the declination axis was moving just a little, but it was. So to understand what was going on, I monitored the XP and YP values. To do that I did the same thing that I did for the Autoguiding issue. I went in the pulse guiding setup and in the function tab I copied 2 buttons. Then I pasted it in the joystick section, which is the consider manual move. You can find that in the function tab. Paste it just before the delay. So you replace the error plus pulse string by the XP and YP value, but it is numbers values, so you have to convert it in strings, and now you can have these values monitored directly on the screen. So now you push just a little the joystick to have the first value, and then you push to the stop to have the stop value. You do the same for the bottom and on the other axis, and then you write all these values to try to understand what's going on. So now I have the 4 values for the first axis. I'm gonna do the same for the second axis. So we already see there is an issue with the axis, because when I move the x-axis from the top to the bottom, we have several values for the y-axis. When the joystick is on the bottom, the y value is 467, and we're going to try to keep in memory this value, because this is the reason of the issue. When the axis is in the middle position, the y value is 497, and it is the x-axis that I move. When the axis is in the top stop position, the y value is 569. So I proceed now for the second axis. Start to move just a little, write the first value, continue to the stop, write the value, and continuing on the other way, and write the 4 values. So if we take a look in the code, in the consider manual move function, which is the part for the joystick, you have 2 values, the XP and the YP value, which are the 2 axes of the joystick. If we take a look in the code, we see there is a minimal and a maximal value for each axis. This is 0 and 1023. But in our joystick, we see that the minimal value was 40 and 80, and the maximal was almost 1000 and 2023. In the code, there is a series of conditions between 0 and 150, 150 to 320, etc. And between 470 and 620, there is no condition, because this is the dead zone, the zone where the joystick doesn't move. Then we continue to go to several values to finish to the maximum value. So here I draw 3 axes. On the top and the bottom you have the real axis of a joystick, and in the middle it is the theoretical axis of the code. Between the 2 arrows there is the dead zone values. Between these 2 values the movement of the joystick will doing nothing in the code. For the 2 axes I've put the min and the max values and make a point in the middle. And what we can see now is the real center of our 2 axes is shifted comparing to the middle of the code. If I display now the 3 values of the y-axis when I moved the x-axis from the top to the bottom, we're gonna understand better what's going on. So here we have the 3 values appear on the y-axis when I move the x-axis from the top to the bottom. This is values of the y-axis. The issue appeared when the joystick was in the stop bottom in the x-axis. The other axis start to move a little. When the x-axis was in the bottom stop position, the y value was 467. But you can see this value is just a little bit outside the dead zone, so the y-axis was moving a little. So here what I did, I redefined the middles, and I redefined the dead zone to be a little bit larger to encompass the defective values. And then I divided by 3 the distances between the minimal or the maximum values and the dead zone. So we obtained the following axis with the following values. You can read on the top, and then you have to write these values in the code. You can see here an overview of the values before and after. Another issue was the GOTO was a little bit slow. Its maximum speed was 1.25 runs per second. I've managed to double the speed. To do that, I went to the slow-to function part, which is the GOTO part. When you scroll down, you see there is a list of conditions that allows to speed up or slow down the motors during the GOTO phase. Then you have the mode step exactly like the joystick part. The lower the number, the greater the speed, but here the smallest is 2. We see in the first condition that when the time is between 0 and 1800, before catching an object or after leaving from this one, the motor is entering in 16 mode. Between 1800 and 2600, the motor entering in 8 mode. There is several conditions until 3400 when the motor's entering in mode 2, and there is the same thing for the deck motor. The motors had a certain difficulty when entering the mode 1 with the joystick function, but I tried anyway to use the mode 1 with the GOTO function, and then running the motors at the maximum speed. Then I modified the code to add a new condition. Between 3400 and 4200 the motor is entering in mode 2, and when the time is greater than 4200 the motor is entering at full speed in mode 1. I prefer to add a new condition instead of replacing the 2 by a 1 to have a smooth acceleration instead of a big jump. Another issue I had was the motors were spinning in the wrong way. For example, the first GOTO I did outside at night, the telescope was pointing in the opposite way of the object pointed. To resolve this issue is quite simple. You can do that by modifying something in the code. No need to desolder or invert some wires. So the first thing is to go to the calculate sidereal range function part and convert the back into forward. Then just below you have the slew2 function, which is the GOTO part of the code. You can use the search function of the Arduino software to look at the forward strings, and then here I've invert the back into forward and the forward into back in this 4 parts of the code. Then if we continue to scroll down, we are in the consider manual move function, which is the joystick part of the code, and here this is the same thing. I've invert all the forward into back and the back into forward for the first axis and the second axis. Then if we look at the next forward occurrence in the code, we go into the pulse guiding setup, which is the Autoguiding part of the code, and here I hadn't changed anything into these strings because when I did all this modification to invert the spinning way of these motors, I hadn't tested the Autoguiding mode, but now it is working, and I had probably invert some wires in the Arduino Nano board, and then as I said, the Autoguiding mode is working, and I don't modify this code now because I don't want to alter the Autoguiding behavior. I did the first Autoguiding test with the webcam mounted on the rDUINOScope, but with the original code, as soon as I plugged the RJ12 connector, the guide star was gone out of the field, so the calibration became impossible. We just seen before that when we restore the tracking, the calibration may be possible. However, the Autoguiding wouldn't work because the mounting was imperfect. I used foam, tape and rubber bands to put the camera on the rDUINOScope. However, I was hoping something with the Autoguiding because the guide star was kept in the crosshair during 45 minutes despite of all these imprecisions. Despite the very low sampling, at a moment I was able to catch a picture at a 2-minute exposure time. Ideally, the sampling needs a rDUINOScope with a 340mm focal length. When I was looking for a rDUINOScope, I was looking the diameter for the sensitivity of my webcam and the focal length. I needed a guide scope with a bar low, which had at the minimum 1 kg on the mount. The mount was already at the maximum of its capacity. I wouldn't add some weight on my mount. The only possibility now is to use an OAG. This is an off-axis guider, which is a piece of optics with an off-axis prism that take a little amount of light of the telescope without hamper the sensor of the camera. So the focal guide length becomes the telescope focal length, which is 1 meter, which is more than necessary for the sampling. Once I received my OAG with all the adapters needed to mount my webcam on this, and with my 600D DSLR, I did a quick test with a PhD2 with the default values on the settings, and I had very good results because I was able to shot 5 minutes and a 10 minutes exposure time picture of M57. The raw shots of this Autoguiding test was pretty good, with a 5 minutes exposure with no rounded shape stars, and the 10 minutes was a little bit deformed, but just a little. I was zooming on it to see the little deformation. I think it's very good for the future of Autoguiding with the rDUINOScope, because the star I used for the Autoguiding was very weak with the low signal to noise. With the brighter star it will be better. So this is the end of this tutorial video. I hope it will make you want to make yours. We've seen that the rDUINOScope is a very versatile system. It has a low power consumption. This is the only system with the touch screen. It has a good pointing and tracking accuracy. It works in standalone and also with Bluetooth mode. It has also an auto-guiding function, and I hope to see it gain in popularity with the respect of its competitors. I made this video as detailed as possible, and I hope that I forgot nothing. So the rDUINOScope is a great stuff, and if you want to have one, go for it!